Good morning, everybody. Good morning. Can you all hear me? Got to be careful now because I need to shout for the ones in the back. So sorry. So, good morning, and welcome. Welcome to basically a bit of a talk on how graph data science can turbocharge your knowledge graph. So my mission really is there to. It's a little bit awkward now. I hope that you can all hear me. I'm going to rely on you to give me the heads up. Thank you. So basically, my mission is to teach you about teaching you about a fascinating world that graph data science can do to knowledge graphs. And so I will talk pretty much a very a comprehensive talk covering many topics today, probably way too fast. But before, and if you have any further questions, then you can definitely come and see us at the Neo4j booth, basically 2 blocks down to the right, stand 328. Before we go into the actual meat and potatoes of today, a word from our sponsors, as it were, Neo4j. Effectively, we were started in 2000 by our CEO and founder, Emil who started to develop an application because they wanted to have a better performance as opposed to relational databases. And so they commercialized the graph database back in 2000. And so in the meantime, our product has developed and our software has developed such that we actually include not only the storage in the graph database, but also the data science aspect as a fully integrated platform, and then the visualization, and then, as I said, offering a fully integrated graph technology platform. So we are the market leader in graph databases by a long stretch. We have a open source software package, a community edition. In the meantime, we have something like 250,000 developers using our software, our database, and also on the enterprise level, many startups are participating in our startup program. We're basically for virtually no cost, you can get an enterprise license, and then we are being used and deployed by many of the largest companies, as you can see here, from eBay to UBS to LinkedIn, deploying us for many applications. Certainly in the biomedical space, we're looking at knowledge graphs, but then for fraud detection in the financial services sector and customer recommendations, etc. Then finally, how can you consume ultimately the software? There is a community edition, as I said, but from an enterprise perspective, there is an on-prem solution and then any cloud provider that you may have of choice. Right, so let's kick it off. In terms of the topics that we'll cover, first of all, we'll cover on knowledge graphs. So we'll give you a context as well as more a formal definition. I think it's more of a formal definition, and then also we'll see some of the how the power of these knowledge graphs, and then the power of these knowledge graphs, and then also how they are being adapted in industry. So that's the first thing of knowledge graphs. Then we look at graph data science, and ultimately what do we mean with graph data science, and what does Neo4j have in the software box. And as I said, this is entirely for you as a free cloud-based solution to use. Then we'll look at graph embeddings, and this is really important. Graph embeddings, and as we'll see, are pretty much the workhorse when it comes to graph neural networks. And so we'll explain the intuitive understanding of a graph embedding. We'll go into node embeddings, and then we'll also see how they can be applied further downstream, etc., with a bit of a use case. Then we'll see how the intersection goes between graph data science and knowledge graphs, and we'll do a toy example there. And then if time allows, and I don't get kicked off the stage here, I'll show you how you can start, again, with a free cloud-based offering that Neo4j has and start on your graph journey. Right, so knowledge graphs. Basically, knowledge graphs is very well captured by a quote here that a quite famous computer scientist, Kristof made to Alan Turing back just pre-war, ultimately, where he said, as you can read, "I'm convinced that the crux of the problem of learning is recognizing relationships and being able to use them." And this is really a really important part, because what he's saying, ultimately, how do we learn? How do we actually learn from, ultimately, what we'll see for today, learn from our data, is really by recognizing the relationships, the links between the entities and the data points. That's a really powerful tool. And then, so that's really what we'll drill down in today. It's not only the explicit relationships between your data points, but it's also the implicit relationships that you can detect thanks to a knowledge graph. And then what we'll see with the graph data science and graph algorithms, etc., to really create semantics around your knowledge graph, generate semantics in pretty much an unsupervised method. So that is really what we'll drill into. just kick it off in terms of like more like a formal definition, and as for those from academia, yes, there is no formal definition yet, but as a working definition, ultimately what we're going to use it for is that it is a structured representation of entities, relationships, and semantics. And so the entities will drill down, we'll give a toy example in a minute. They can be very basic things such as people, person nodes, or cars. So those are the nodes, the vertices in our model. The relationships, of course, are the explicit connections between those data points. And again, we'll show a toy example. And then it really, I wouldn't say it comes down to, but the semantics form a very, very important component here. And as I said, the semantics, what we'll show is how to learn from your network structure, from your topology in an unsupervised manner through and thanks to the algorithms and the models that we have. And so that is really how we define the knowledge graph, but also how we can incorporate it within the data science aspect. So just to basically give you the intuitive understanding of a knowledge graph and how to think of a knowledge graph, and then you can basically abstract it to your own problem in a data set. So we're starting basically with 3 nodes, as you can see here. In the Neo4j lingo, we have 2 node types. We have a people node, a person node, and then we have a car node, okay? And so the first thing we'll do is add some semantics as sort of like unique identifiers to those nodes. And so a simple one is that we're adding name, Twitter, birthday, Twitter account, etc. As I said, I may have said, I'm not sure I said, we are a Swedish company, hence we all drive Volvos, of course, and then we can define the relationships between those nodes. But one thing I would want to stress is the properties that we've defined here are sort of like just the unique identifiers of those properties. The key thing when it comes to graph machine learning, embeddings, etc., is to generate properties that you've learned from your network structure and then write them back as a property to those nodes. And that is what we mean with semantics. And we'll see later on how we can do that. So we're now going to define the relationships. And again, semantics can also be defined in the relationship type. So Dan is in love with Anne. He's a lucky fellow because she loves him back. Happy days. And they're living together. Great stuff and all of that. Then they've got the car here. He is driving the car. Obviously, she paid for it. And so now we have basically defined the knowledge graph. But one thing that we can also do is add more semantics to the relationship type. And so a simple example would be that we're adding here, he's been driving the car since January. Great, but what could we do, which is more powerful, which we can use in the graph algorithms, is adding a weight to that relationship. So we could say he's driving the car 5 days out of 7. So you have now a weighted relationship, which can come back in the graph algorithms that we'll use later on. So that's it. You now have in its most basic form a knowledge graph. That is nodes, the connections between those nodes, possible multiple relationships between those nodes. And so you can abstract this to your own project. These can be customers, these could be particular targets that you have, these could be parts in your supply chain or in your production, etc. So those are the kind of things that you can do. So this is how you construct ultimately a knowledge graph. And then basically the thing with the knowledge graph is, as opposed to say a tabular format, the beauty of a knowledge graph and the power is that they grow. They grow. Knowledge graphs grow. And let me just showcase that in a very, very simple example. So we have here 9 nodes, 9 very simple nodes. And so there's a few things that stand out here, because with the knowledge graph, ultimately, it grows by detecting these implicit relationships, as I mentioned. And if you look at this toy example, have like a 5-second think about it. What stands out that you could say is implicitly that you can derive from that knowledge graph? I'm afraid we don't have a microphone that is quick enough, but if you shout it out, then I'll repeat it on the microphone. So if you now look at those two users, they're serving the same websites, but is there anything else that sort of like stands out that you could say, oh, implicitly there's something going on here?
We have them.
Shout it out. No, but they're using the same IP location, so guess what? They're still using the same laptop, using the same iPhone. Yeah, they're probably the same, right? So implicitly, we're finding the same people here, the same application. And that is the beauty of storing your data is a graph data structure in a graph database, because imagine you don't have 9 nodes, but you have 900 million nodes or 1.9 billion nodes. Then through the graph database and the query language that comes with it, and this application or this technology called index-free adjacency, which we can explain later on, you can search your graph in literally milliseconds. And you can say to the query language, go and fetch me all of those nodes that have it in common, and then return me those nodes, and with one line of code, I can then tell the query language, make me those nodes that are implicitly the same, explicitly the same, right? I can now create a relationship between those two nodes. So this is very much in a toy example, but imagine now that you have, as I said, 900 million nodes, 1.9 billion nodes, and you don't need to do this, you can't do this in a tabular format, right? Because then you will need to construct X amount of joins. So that's what we mean with ultimately implicit relationships can be detected in a knowledge graph and can be made explicit. By making them explicit, by establishing that relationship between those data points, your graph grows organically. You get ever more insights in your data, enriching your data as such. And this is really the power of a graph, of a knowledge graph, and storing it in a graph database and letting it run like that. So, and consequently, knowledge graphs, it's not just us who's saying that. Of course, you must be thinking, all of these guys at Neo4j, they have mushrooms for breakfast. They only think in knowledge graphs. But if you look at industry, you see a wide adaptation. And that's why you can possibly, after today, you can have a think about how you can incorporate it. So one of the most vocal about the application of knowledge graphs is JP Morgan. They're actually publishing several papers. And in this paper, they basically, how they do credit risk analysis. And if you want to know more about it, come and see me afterwards. But in this paper, they're also stating, look, knowledge graphs are becoming mission critical across many industries. And certainly, of course, as I said, we're not just saying that. If you now look at many academic papers are evidencing how knowledge graphs are being used in manufacturing, in production, in medical, biomedical space, which we'll see later on. So they're really becoming ubiquitous. And why? Because as you just saw, they're very powerful. You can detect implicit relationships and learn more from your graph structure. At Neo4j, we're very proud to have worked with a lot of these use cases, a lot of these companies, and we have a ton of these use cases that you can look on our website. But as I said, we eat, sleep, and drink knowledge graphs. So if you're interested, come and see us at our booth 328. Basically, if you go outside here, 2 blocks down to the right, and then you can get your free copy on knowledge graphs, which elaborates a little bit more on the theory and applications of knowledge graphs. So come and see us. Right, so now that we sort of like have defined knowledge graphs, what can we do ultimately with graph data science? What do we mean with graph data science? And ultimately, and what do we have in the box, as it were, at Neo4j that you can use? So when we talk about going from implicit to explicit connections and relationships, we basically see this in a 3-step approach. So already through the query language, you can detect these patterns. So the toy example that I just gave you, that is just deploying the query language, right? And then the power really of the algorithms and the models is that you can now use these to detect implicit relationships which are totally non-obvious. And so in first instance, we will draw upon the graph algorithms that are basically been developed in graph theory over the last couple of decades, and we'll see a few examples of that in a minute. So we have the set of graph algorithms, and hopefully we'll be using Neo4j, but in general, that is what is being done in ultimately graph data science. You will deploy some of these centrality metrics, community detection, etc. And then in that final step, we'll look at graph embeddings or node embeddings, and then the machine learning that come with it. So those are effectively the 3 steps that allow you to detect implicit relationships and also then eventually make predictions. So what we have at Neo4j and what is all at your disposal, we have basically now to 65 and close to 70 algorithms soon, and they are sort of like organized around 6 pillars. And so, of course, when you have a graph, you want to do a fast, shortest paths, etc. And again, imagine you have a graph of millions and billions of nodes, then you want to find shortest paths when it comes to supply chain or all these kind of things. Then we also have what we said the graph algorithms. And so those are like the bread and butter, as it were, when it comes to graph theory. So we have a set of centrality algorithms, and we have a set of community detection algorithms. And so we probably use a centrality algorithm at least 10 times a day. And any guesses? Oh no, it's very difficult, I suppose, now. Which algorithm we probably use, which centrality algorithm? I think the lady here said, like, indeed, search. Whenever you do a search, you go to Google, you deploy PageRank. So, so PageRank algorithm is something we use every time, several times a day. What does it do? It looks at your network structure, it looks at your graph, and it computes a score for each node in that graph in function of how it is connected to other well-connected nodes. And that's ultimately how they started with the whole search engine. So decentrality algorithms, very powerful. Again, in an unsupervised way, you can learn from your network structure, from your topology, you can compute a score, and then this comes back to the semantics. You can use that score and write it as a property to the node. So we saw Dan, Anne, and their birthday. We can also add their PageRank score, for instance, right? So those are the things, and that's what we mean with feature engineering and ultimately creating and learning semantics. So there's a bunch of community detections algorithms as well. And again, what do? They cluster the nodes in function of the algorithm that you want it to do, that you tell it to do, but it works again in an unsupervised way. Very powerful. If you haven't structured your data as a graph, loaded in a graph database, those algorithms are not at your disposal, and you won't be able to learn from your data structure. Then, as I said, so like the workhorse when it comes to graph machine learning, deep down in the engine room, as it were, is some form of embedding technique at play. And for that, we have these algorithms as well. We'll see them later on. In a nutshell, as a working definition, what does it do? It takes a node and it basically represents that node as a vector. So that's a long list of numbers in a vector space. And then once you have a vector, then ultimately you can, and then of course you can deploy a lot of these distance measures to compare vectors. And for that we have cosine similarity, k-nearest neighbors, and a bunch of similarity algorithms in there. And so that is basically the whole set that you can do. However, before we go any further, so we're going to do a little quiz, and my suggestion is, I appreciate we have the headphones, but maybe you can collaborate a little bit with your neighbor. It's also a good way to make friends, to network, and so I'll let you think and talk a little bit for like a minute or so, and then shout it out whatever you think, right? It's a large audience, but I'll repeat it. Okay, here we go. Ready? If you now look at this graph, just look at the entire graph. And if you were asked to consider only the colored nodes, so D, G, and I, and then to list which node you would think is the most important node in this entire graph. So consider all of the graph, but only think of the D, G, and I as the most important nodes. Make friends, make friends. I'm going to have to pick on some Chinese volunteers here because we're running out of time. So the gentleman here, because what do you think? I think it's G. G. The gentleman goes for G. Any more takers for G? Raise your hand. Yeah, a couple of things. Who's going for I? Raise your hands. I. Ooh, many go for I. Who goes for G? G. Yeah, some takers for G. Who goes for it depends? Yeah. Well, indeed, it depends what you want to measure, right? So all of these were good answers, and let me explain what they do. What we've just done here, we've just deployed, you deployed a centrality metric. You just analyze it from a centrality metric. So I, for instance, and so many people will go for I. Why? Because it's what is called a connector point. And how do you compute that? How do you score that? By between a centrality. So you can deploy these algorithms on your large graph. Remember, it's on your large graph, and then rank your nodes that lie on these bridges. Of course, this is a toy example. You can immediately pick out which is a connector point. But imagine again, you're looking at thousands, millions, billions of nodes, and then there's multiple ways of doing that. So I is high between a centrality score. If you take out I, if you're a telco company and you have a bunch of routers, you want to make sure that I gets protected, right? That doesn't go down, because the whole thing goes down if you do that. Node D has the highest connections, and node G is if you're a bank manager and you need to close down branches, you're going to look at G. Why? Because it's closest to all the other nodes, right? So you don't want to close down bank branch G or post office G, because that one is the nearest to all the other ones. So this is something you can learn. Just wanted to let you think a little bit about how graphs and how you can graph algorithms, etc., can work on your graph. And again, here you can use those scores on a standalone basis, as it were, but more equally important, which we'll see, you write them back as a property to the node, which we then will be using in our embeddings. We'll see that in a second. And so that's basically what we're going to do now. And it's a little bit of a misnomer here when I say from chaos to structure. That's not really the case. But what we're ultimately trying to do, the thing with a graph is, the power of a graph is that it's flexible, but also what it is, it's what is called non-Euclidean. That is to say, you cannot overlay it with a XY coordinate system with a grid structure. So researchers had to find a way to take this graph, which is sort of like trying to nail jelly to the wall, and to convert it in some form of numerical representation. And that's ultimately what we're doing with an embedding, right? We'll see at the models in a minute. But in a nutshell, we take a node, we take its connections to its neighbors, so its neighborhood, and you determine how deep that neighborhood is. And then whatever feature information I have for each node, all of that information gets represented in a graph, in a vector, ultimately. And so for that we have so this is a pictorial example, so we have node U, and we represent it as a vector. For that, in Neo4j, we have 3 models. For those a little bit familiar with natural language processing, word2vec. Word2vec is a method that has been extended to the graph space, and then hence we have node2vec. Word2vec has been extended to the graph space, and that's how we got node2vec. And then we have 2 other models, GraphSage and FastRP. GraphSage and FastRP allow you to take into account any features for each node, whereas Node2vec only looks at a neighborhood. And again, if you're interested, we have a ton of documentation, we have a ton of Jupyter notebooks. Come and see us afterwards, and we can elaborate a little bit on that one. And then so we have now we have vectors, right? Now what? Now what? Well, for those who are trained in traditional machine learning, it's happy days. You're off to the races, right? Because now, if you have a vector, and suppose now that you've developed some ground truth labels around those nodes. Let's suppose you're a bank and you're a financial crime department, and over time your caseworkers have basically manually figured out that this kind of behavior, these kind of nodes, these kind of politically exposed people are high risk nodes. And so once you have converted your nodes to a vector, you have some ground truth labels, you can now train a traditional machine learning workflow to learn the association between the vectors and your target variable, right? So now in traditional machine learning land, we know this space, right? We know what to do here. The way you can do it through Neo4j is ultimately through a pipeline structure. So we have 3 workflows. We can do node classification, we can do link prediction, and we can do node regression. That is done through a pipeline, as I said, and then it will deploy a bunch of models that we have, and it will select the best model for you, either multi-layer perceptron, random forest, or linear regression, and many more to come. What else is important? We have the vectors. So you can use the machine learning pipelines and the workflows that are in Neo4j, but you could also say, thank you very much, Neo4j, but I want to run my own classifiers, either my own neural network. Well, everything that you see here in Neo4j can be done straight into your Python environment. You get your vectors in your Python environment, in your local memory, and then you can run whatever classifier you would like to do. We have a ton of examples where we've done it, where we've basically worked with constructed a TensorFlow neural network, a neural network model in TensorFlow, etc. So come and see us afterwards. We also have examples with scikit-learn, so you can do the classification on your own and you don't need the pipelines, etc. And so one thing I wanted to highlight and hopefully get the enthusiasm that I feel for it across to you is this combination of ultimately this workhorse that an embedding is, and then marry that and attach that to a neural network, integrate it with your neural network. That gives you a graph neural network, and those models, as we saw and as we see, learning from the network structure are extremely powerful. If you now look what is going on in machine learning research, this is a little graphic that we took from the papers that were submitted to one of the major machine learning conferences, namely ICLR last year. If you look at, this is a comment that Kristof Manning, who's a professor at Stanford, commented, that huge rise in reinforcement learning. Yes, we know how powerful they are, AlphaFold, but then as he's commenting, graph neural networks are in the top 3. So in terms of machine learning, graph neural networks and reinforcement learning are really the area you want to focus on because they are so powerful. And there's a bunch of examples that we can talk about later on if you're interested in terms of what's going on in biomedical space, in academia, etc., etc. And then quickly to wrap it up, integrating all of those algorithms and those models with the knowledge graph, and again, those are the semantics, etc., is truly a marriage made in heaven. And so I lifted this graphic from one of the survey papers on knowledge graphs. And as you can see here, the applications of knowledge graphs, then combined with a lot of the neural network models and all the kinds of other things, allow you to do many workflows. And for instance, knowledge representation learning is something like the embedding techniques that we just talked about. You can expand them, you can really represent your graph now as a vector, and etc. Knowledge acquisition, we'll see a toy example of that in a minute. Knowledge graph completion is a classic workflow. And then also knowledge aware applications. What are they? Those are chatbots. And so one of the largest users that we know, that I know of at least, is Alibaba and the financial firm Alipay, I believe. They developed a chatbot based on a knowledge graph with a graph machine learning on top of it, managing to retain 90% of all questions in the chatbot. So not having to go to a worker. So very powerful applications. And then we also have a temporal graph application, etc. And so now, as I have 5 minutes, so I'll try and be quick. So just to give you an example of ultimately what this knowledge graph completion can be. So let's suppose now we have this little toy graph. Obviously everything centers around Elon Musk these days. So like the Copernican revolution is slightly revised. And so if you now look at a bunch of these nodes, so you have solar power, you have cars, you have machines, and you have the connections between them. Obviously Elon Musk, even he can't do without solar power, so he's fueled by solar power. We know that solar power is an energy source. Elon Musk, we know he makes cars, and the car is a machine. And then we have this like little planets floating about, Mars and planet. And then so you really can develop now a graph machine learning, a graph embedding, and link prediction model, which you can do in a Neo4j environment, to basically try and infer from the information that you have what Elon Musk is all about, right? And so you could say, Elon Musk, is he now a human or a machine? I just introduced the human nodes. So you don't know, we don't know, right? I mean, who knows? And then what is his relationship with Mars, right? What is that? Does he want to go on holiday there, or was he maybe born there and maybe he wants to go back, right? Who knows? We don't know. But the machine learning models can help you with that. And then so really to wrap it up, and we're a little bit tongue-in-cheek now, one of the things that is really hot in the general machine learning space are language models, right? Transformers, language models, very, very powerful. Now, the integration and the use of language models to create and construct knowledge graphs is really extremely powerful, and luckily being applied now in the biomedical space. And just to give you an idea, we have done an example, we have done a demo, come and see us afterwards, in how to integrate a language model and then use it to populate a Neo4j graph. And again, you guys can say, these Neo4j people with all of their mushrooms, I don't believe any of it. But if you look at what these researchers have done in the biomedical space, these guys are totally unknown to us. They've used a bird language model to do named entity recognition, extract the key terms, and then, happy days for us, use Neo4j to populate the database and use some of the algorithms. So as I said, we have our software is open source, community edition. There's a ton of these papers available. What is so cool about these papers is that you can see how they've done it. Often they've published their code on GitHub, and so you can see that workflow happening. And then so one last thing, how to get started on your graph journey. I think I've got 1 minute left. As I said, all our software is free to use. The best way to start, the easiest way to start, literally within less than 5 minutes, is to go to Neo4j Sandbox. It takes a couple of minutes to get your credentials, to register, get your credentials. And there you can upload your own data, so you can start a blank database. But in addition, there's about 12 preloaded data sets ranging from the Paradise Papers, these are the Panama Papers with all of these fraud people, etc., up to fraud detection data sets. And what is also very cool about it is that some of these data sets have preloaded demos. So you can do a self-paced demo with a script that then runs itself, and you can see how you need to use the code, and the results that come with it. And then one final step is that there is everything that you see here. All of those demos are probably somewhere in a Jupyter notebook. So as I said, we fully integrate with Python. Also other languages such as Java and JavaScript, but from a data science perspective, we have a ton of demos, ton of Jupyter notebooks, and so that you can then use our, what we call the Python connector, to run any of the algorithms, the whole database, anything you want to do in Graphland in your nice and cozy Python environment. And so, yeah, that's basically what I wanted to tell you today. So if you have any further questions, come and see us at the booth 328. I thank you very much for taking the interest to learn more about graph, machine learning, and knowledge graphs. And as I said, I'm there at 328. And thank you very much. And I wish you a very good morning for the rest of the day. Thanks.